Hi, welcome back. We're in lecture 15, segment 2, and the topic of this lecture is t-tests. In segment 2, we'll cover dependent t-tests. So, as I mentioned in segment 1, a dependent t-test, which is also known as a paired samples t-test, you'll see that phrase in the R output. It's appropriate when we have the same subjects or the same cases, doesn't have to be people, the same subjects or cases measured twice, so we can calculate a different score for each individual subject and then look at the mean difference score. You could also use it, it's not as common, but you could use it if you have very well matched samples. So if you have samples that are matched at the level of individual, then you can calculate different scores at the level of individual, in which case you can do a dependent t-test. Again, the idea is that one measure is dependent on the other. They're related. So a thorough analysis, and I'm going to try and encourage you to do thorough analyses when you engage in not just t-tests, but any kind of statistical analysis you might do going forward. A thorough analysis will include not just the t-value, but of course the p-value if you want to do NHST. But of course there's problems with NHST, so let's throw in a measure of effect size. And in this case it's going to be Cohen's d. That's a new concept which I'll cover. And again, we could do interval estimates as well, because remember, these sample means are just point estimates. So to review, the t-value is just an observed minus an expected over standard error. The observed is just the mean difference score. So again, we calculate a difference score for every individual and then average them. That's the mean difference score. What's the expected value? Well, we're playing the game of NHST, so the expected value is 0. So that just falls out of the formula. So t is real simple. It's just the mean difference score over the standard error of the mean difference score. That's it. So what did you observe relative to what would you expect just due to chance? That's it. Real simple. And again, the p-value will be based on that t-value and which t-distribution you're in and whether you're doing a non-directional or directional test. But again, that's an NHST, so it's biased by sample size. So you should supplement that with an estimate of effect size. And effect size is different here than it was back in regression. Now we're going to calculate what's called Cohen's d. And the formula for Cohen's d is real simple as well. It's just the mean difference score over the standard deviation of the different scores. So notice that the slight difference between t and d. T we're dividing by standard error. Here we're dividing by standard deviation. Why is that? Well, standard error, if you remember, is the standard deviation over the square root of n. So it's biased by n. As we drive n way up, standard error goes down, which means t will go way up, your p-value will go down, just as a function of n, right? That was the problem with NHST in general. Here, this effect size estimate, Cohen's d, is very clever. It doesn't go to that extra step of calculating standard error. It just does it at the level of standard deviation. That's not biased by n. Plus, it's a very intuitive measure. It just tells me how much, in terms of standard deviation units, does one mean differ from another. Or if we're looking at change score, like we are here in a dependent t-test, it's how much did people change from one measurement to the other in standard deviation units. So Cohen's d of 1 means that people went up a whole standard deviation. That's a pretty big effect. And again, we can get interval estimates around these means rather than just point estimates. So we could get the mean of the different scores, but then put an upper bound and a lower bound on an interval. And we get the upper bound and lower bound just like we did before when we were looking at confidence intervals for just sample means or regression coefficients. We want to add some function of standard error, and we multiply standard error by t. That exact t value depends on how confident we want to be. So like a 95% confidence interval versus a 90% confidence interval. And it depends on which sampling distribution of t we're going to use, because we have that family of t distributions. So it depends on the number of subjects in the sample. So to illustrate dependent t-test, I'm going to walk you through two examples that we've used already in the course. First, wine ratings, and then the working memory training experiment. So let's look back at the wine ratings. So if you remember, we had wine experts from 4 different countries, right? And each wine expert rated 2 wines, 1 red, 1 white. So since we have 2 scores from each individual, we could do a dependent t-test to see if there's a significant difference in the mean ratings of red versus white. Now, we're going to do that on the Australian ratings because Australia was the only country that produced a normal distribution in the white wine ratings. Remember, all the reds were normally distributed, but then to show non-normal distributions, the whites were all messed up, right? But in Australia, the white distribution was normal. And one of the assumptions underlying this test is that we have normal distributions. So we're just going to do this example on the Australian wines. So here are the data in a bar plot, and it's just a slight edge for the white. So they're just like a couple points higher than the red. So on average, these wine experts in Australia like the white better than the red. But is this a significant difference, or is this difference just due to chance? So if we had them do it all over again, would it come out slightly differently, like the red would be slightly higher than the white? So that's the question. Is this a significant difference, or is this just about as much of a difference as we would expect just due to chance because of sampling error? So we can test that by running a dependent t-test in R, and we'll do this in the next lab. So it's really simple. There's a function called t-test, and we just put in the 2 variables that we want to compare, but then we have to tell R that we're doing a dependent test. And again, R uses the term paired t-test for dependent because the 2 variables are paired in some way. So we have to set paired equal to true. So that's the last argument in the t-test function. So we do that, and now let's look at the output. Here's the actual t value. It's negative 8.0217. Why is it negative? Well, just because I put the red first and the white second. It's completely arbitrary in this case. I could have flipped them around and it would be positive 8. Doesn't really matter in this case. But you see, that's a high t-value. So even though on the graph it looked like a small difference, it's a reliable difference, at least in this sample. The degrees of freedom of 99, that means there were 100 wine raters, right? Because degrees of freedom is number of cases minus 1. There's our p-value. It's off to 12 significant digits. It's less than 0.00001. Very, very low. What R gives you is a confidence interval, but a little different from the confidence intervals that we covered back when we had the whole lecture on interval estimates. So what R gives you is not an interval around like the mean of the red and the mean of the white. It gives you an interval around the mean difference. So here is the actual difference. It's a difference of about 5 points. And the interval is from about 3.8 to 6.3. So again, this is our point estimate. This is our interval estimate. What's important about that interval estimate is it does not include 0. That tells you that it's going to be significant in terms of null hypothesis significance testing. Then finally, at the end, there's a function in R, which we'll cover in lab, called Cohen's d, where we can get that estimate of effect size. And the Cohen's d in this case is 0.8. That's pretty strong. There's almost a full standard deviation difference between the reds and the whites. Not quite 1, but 0.8 is a strong effect. Okay, now let's do the same thing looking at the working memory training example. We can compare intelligence scores before training and after training, just in the training group. So that's what we're going to be doing here. Remember, there was a training group and a control group. Just for ease of illustration, doing a dependent t-test, I just want to show you a pre-post comparison on the training group. And again, the question was, did their intelligence go up as a function of training? So here's what it looks like in a bar plot. It looks like, yeah, they went up a little bit. But again, the question is that a significant difference, or is that just the magnitude of that difference just what I would expect due to chance? Well, let's look at the output. Again, it's just the function t-test with pre, post, and paired set to true. Here's the t-value. It's 3.5. Again, think about those sampling distributions. 3.5 is way out there in the tail. So again, really low p-value. Yes, this is significant. And again, to be thorough, we have our interval estimate, and we have our estimate of effect size, Cohen's d. Coincidentally, it's about 0.8. I didn't plan that, so the wine rating effect and the working memory training effect are about the same magnitude, despite the fact they have different sample sizes. Right? It's actually a good lesson that the effect sizes are about the same, but the p-values are very different, right? The p-value here is not so low because the sample size is much smaller. Didn't plan that. That's a nice coincidence. So to sum up this segment, dependent t-tests are appropriate when you have the same subjects or same cases that are measured twice, so you can calculate different scores. And a thorough analysis is going to include the t-value, the p-value, if you want to do the null hypothesis significance testing, an estimate of effect size. In this case, the most appropriate one or most common one is Cohen's d, and you could also report interval estimates rather than just point estimates.